7 minutes ago, somewhere in a windowless facility in Santa Barbara, California, a machine with no keyboard, no monitor, and no screen finished a calculation that, by every rule of classical physics, should not have been possible in your lifetime. Not in your children's lifetime. Not in 10,000 lifetimes stacked on top of each other. We're talking about a number so large it doesn't just exceed the age of the universe. It makes the age of the universe look like a rounding error. And the strangest part? The people who built the machine aren't entirely sure what to make of it either. Let's start with the facts, because the mainstream coverage buried the real story under a wall of jargon and hype. Google's quantum computing division built a processor called Willow, a 105-qubit superconducting chip manufactured in-house at Google's own fabrication facility in Santa Barbara, and unveiled to the world in a peer-reviewed paper published in the journal Nature. On paper, that sounds like a routine hardware announcement. Another chip, another press release, another line on a spec sheet. But the physicists who actually read that paper weren't celebrating. They were recalculating. Because Willow didn't just set a new speed record, it broke a wall that had stood untouched for almost 30 years. Here's the number that should stop you in your tracks. Google ran Willow through something called random circuit sampling, widely regarded as one of the hardest benchmark tasks you can throw at a quantum processor. Willow finished it in under 5 minutes. 5 minutes. Now hold that number in your head, because the comparison is where reality starts to bend. Google says that same task, run on Frontier, one of the most powerful supercomputers currently operating on Earth, would take an estimated 10 septillion years to complete. Write that number out and it looks like this: 10,000, 1,000, 1,000, 1,000, 1,000, 1,000, 1,000, 1,000. The universe itself is roughly 13.8 billion years old. Willow compressed a task that would outlast the universe by a margin almost too large to describe, into less time than it takes to brew a pot of coffee. But, and this is the part almost nobody talks about, the speed was never the real story. The real story is buried in something far less flashy and far more dangerous to the status quo: error correction. Here's the dirty secret of quantum computing that the entire industry has spent decades quietly wrestling with. Qubits, the quantum equivalent of a bit, are almost impossibly fragile. They exist in delicate quantum states that can be destroyed by a stray vibration, a whisper of heat, a single photon in the wrong place. For 30 years, the deeper problem was this: the more qubits you added to scale a machine up, the more errors you introduced. More power meant more chaos. It was a trap the entire field seemed permanently stuck inside, a ceiling nobody could break through. Willow broke it. Google demonstrated that as they scaled their qubit grid up, from a 3x3 array to a 5x5 to a 7x7, the error rate didn't rise. It was cut in half at every single step. The machine got more accurate as it got bigger. That is not a small improvement. That inverts a problem that has haunted quantum computing since error correction was first theorized by physicist Peter Shor back in 1995. For the first time, Google says, a processor demonstrated real-time error correction below the critical threshold needed to make large-scale quantum computing physically viable. The core physics argument against ever building a truly large-scale quantum computer, the argument skeptics have leaned on for 3 decades, just lost its foundation. And then the founder of Google's quantum division said the sentence that pushed this story out of physics journals and into the wider public conversation. Hartmut-Neven looked at Willow's results and said they lend credence to the idea that the computation might be occurring across parallel universes, a controversial interpretation of quantum mechanics first proposed by physicist David Deutsch decades earlier. Is that proven? No. Plenty of physicists pushed back immediately, and we'll get into exactly why in a moment. But think about what it tells you that one of the most credentialed scientists in the field, standing in front of his own machine's results, reached for the multiverse to explain what he was looking at. When was the last time a chip announcement did that? Now, if part of you is skeptical right now, good, you should be. Because Google has been here before, and the last time it made a claim this big, the claim didn't fully survive contact with its critics. There's a very real, very legitimate counter-argument to everything I just told you, and it's coming next. But here's the twist that changes everything about this particular chapter of the story. What happened after the skeptics spoke up, and what Google published less than a year later to answer them directly. Here's the legitimate counter-argument, and you deserve to hear it in full before we go any further. Random circuit sampling, the benchmark Willow used to set that jaw-dropping speed record, is, by design, a task with no real-world application. It's essentially a very elegant, very expensive stunt. Critics pointed out that the randomness baked into the test made it nearly impossible to independently verify the results against another system. In plain language, the machine did something impossibly fast, but nobody outside Google could fully check the work, and the task itself didn't help cure a disease, design a battery, or do anything useful for a single human being on Earth. Even NVIDIA's CEO Jensen Huang publicly suggested that genuinely useful quantum computing was still decades away, and Google had already been burned once before. Its 2019 quantum supremacy claim was later challenged, when classical researchers found ways to optimize the same task and close the gap. The skeptics had the high ground, and they'd earned it. Then, in October 2025, Google took that high ground away. Google announced a new result. For the first time in the company's history, a quantum processor successfully ran a verifiable algorithm on hardware and beat the fastest classical supercomputers on Earth by a factor of roughly 13,000. Verifiable. That one word changes the entire conversation. The algorithm is called quantum echoes, and when Google's team ran it using 65 of Willow's qubits, it completed the task about 13,000 times faster than the best classical method running on a supercomputer, with results published in Nature, arguably the most scrutinized scientific journal in the world. No more hiding behind unverifiable randomness. This time, the answer could actually be checked, and it held up. But quantum echoes wasn't built to win an argument. It was built to do something. Google says the algorithm can help map the structure of physical systems, from molecules to magnetic materials to the extreme physics around black holes, with a level of precision that classical computers simply cannot reach. One member of the research team described the leap in blunt terms. Back in Google's 2019 demonstration, only about 0.1% of the data gathered was actually correct. In this new result, only about 0.1% of the data was wrong. In 6 years, they didn't just improve the machine, they flipped it. And they immediately pointed that precision at something real. In a separate proof-of-concept experiment, Google's researchers demonstrated what they're calling a molecular ruler, a technique that uses quantum hardware to measure molecular distances, more precisely than existing methods allow, drawing on data from nuclear magnetic resonance. In early tests, using just 15 qubits, the approach produced accurate models of molecular structure, and researchers believe the method could eventually have broad applications across chemistry, biology, and materials science, given how widely NMR is already used in labs around the world. Translation. This is the early groundwork for a machine that can see inside a molecule with a clarity no classical computer has ever offered. New drugs, new materials, new batteries, new catalysts, an entire hidden layer of the physical world, potentially cracked open. That is the bright side of this story. And if the story stopped here, this would be a very different kind of video, a hopeful one, a purely scientific one. But it doesn't stop here. Because buried inside the same research pipeline that produced quantum echoes and the molecular ruler is a second thread, one that has nothing to do with medicine or materials, and everything to do with the locks currently protecting your bank account, your medical records, your private messages, and the classified communications of governments around the world. In March 2026, a set of research papers landed, one from Google's own quantum team, another from a quantum computing startup working alongside researchers from Caltech. And the conclusion inside them was blunt enough to wake up cybersecurity professionals who don't usually rattle easily. The encryption protecting the modern internet, they suggested, may be crackable sooner than almost anyone in the field had planned for. One cybersecurity researcher at Cloudflare, a company that secures a meaningful share of global internet traffic, called the findings a real shock. And the response wasn't theoretical hand-wringing. It was immediate, and it was measured in hard deadlines. Cloudflare moved up its own defense timeline. So did Google. The company building the machine that might one day break the internet's locks looked at the official government safety deadline and decided it was years too slow. We're going there next, because once you understand exactly what breaking encryption actually means for you, personally, this stops being a science story entirely. Let's slow down on that sentence, because it deserves to be said plainly, without the corporate softening it usually gets wrapped in, the encryption protocol securing the internet, your bank account, your medical records, your government's communications, military systems, cryptocurrency, all of it, rest on mathematical problems that classical computers cannot realistically solve. That assumption is the foundation of digital civilization as we currently know it. And Google's own research just put a visible crack in that foundation. Here's exactly what happened. On March 30th, 2026, Google's quantum AI team, working alongside researchers from Stanford and the Ethereum Foundation, published a detailed white paper analyzing the quantum threat to elliptic curve cryptography, the specific type of encryption underpinning digital signatures across banking, secure communications, and the cryptocurrency networks behind Bitcoin and Ethereum. The headline number: Google's researchers compiled quantum circuits capable of breaking 256-bit elliptic curve encryption using fewer than 500,000 physical qubits, roughly a 20-fold reduction compared to earlier estimates from just a few years prior. Under standard hardware assumptions, they estimated those circuits could run in a matter of minutes on a sufficiently advanced quantum computer. Read that again. Not a reduction of 10%, not a reduction of half. a 20-fold drop in the estimated resources needed to break the encryption that protects a meaningful share of the world's digital value. And in a notable twist, Google didn't even publish the actual circuits. Instead, the team used a cryptographic verification method called a zero-knowledge proof, allowing outside researchers to confirm the circuits work exactly as claimed without revealing the blueprint itself. Google says it engaged with the US government before publication, and is now urging other research teams facing similar discoveries to adopt the same disclosure approach. Around the same time, a separate research collaboration involving Caltech, Berkeley, and a startup called Oratomic explored the same threat from a different angle: neutral atom quantum computers instead of superconducting chips. Their estimate was even more aggressive. A machine with somewhere between 10 and 20,000 atomic qubits could, in theory, implement the algorithm needed to break this style of encryption. One of the paper's co-authors put it without any corporate hedging at all: there is no question that we used AI to accelerate this development. Artificial intelligence didn't just watch this breakthrough happen from the sidelines, it helped build it. Now, before this spirals into panic, you deserve the honest caveats. Because this channel deals in reality, not fear. The paper has not yet completed peer review, and several outside experts, including a Princeton associate professor who studies quantum hardware, have pointed out that some of the underlying assumptions remain untested. It's relatively easy to shrink your resource estimate on paper if you assume future qubits will be cleaner and more reliable than anything that currently exists. Today's quantum computers are nowhere near large enough or stable enough to actually execute an attack like this. Nobody's Bitcoin wallet was drained this morning. Nobody's bank account was silently compromised last night. But that reassurance comes with an expiration date, and the industry knows it. A widely cited 2025 survey found roughly a 1 in 3 chance that a cryptographically dangerous quantum computer could exist within the next decade. And the risk isn't only about machines getting bigger, it's about the algorithms getting more efficient, which means the size of machine actually required to cause damage keeps shrinking. The wall isn't just being climbed, it's being lowered at the same time. And that brings us to the threat almost nobody outside the intelligence and cybersecurity world talks about openly. Harvest now, decrypt later. It means the attack on your data may have already happened, and you simply don't know it yet. A hostile actor doesn't need a working quantum computer today to hurt you in the future. It only needs storage. Intercept encrypted traffic now. Financial records, private communications, corporate secrets, diplomatic cables. And warehouse it and wait. The moment a sufficiently powerful quantum machine comes online, years of stolen encrypted data instantly becomes readable plain text. According to the Cloudflare researcher who called this a real shock, the arrival of a capable quantum computer ahead of a completed transition to post-quantum encryption could trigger data leaks, extortion campaigns, and outages across businesses that never saw it coming. Because nearly every system on Earth built on today's encryption standards becomes vulnerable at once. This isn't a future crime. It's a present crime with a future payout. And the reaction from the people closest to this technology tells you everything about how seriously they're taking it. Days before these papers were even published, on March 25th, 2026, Google announced it was accelerating its own internal timeline to secure its systems against quantum attacks by 2029, 6 full years ahead of the 2035 deadline set by the US National Institute of Standards and Technology. Cloudflare made a similar move, pulling its own defense deadline forward. Meanwhile, Bitcoin's own developer community merged a formal proposal, known as BIP 360, earlier this year, laying early groundwork for a quantum-resistant upgrade path, while the Ethereum Foundation has spent years building out a dedicated post-quantum security roadmap, aiming for full migration by the end of the decade. Think about what it means when the company building the most advanced quantum hardware on the planet looks at the government's official safety deadline and decides, on its own, that it's too slow. And decides on its own that it's too slow. That's not marketing. That's not hype. That's a company quietly preparing its own bunker years ahead of the schedule it's telling everyone else to follow. So who's actually racing to build the machine that could turn this theoretical threat into a real one? And how close are we, right now in July 2026, to it actually happening? That's where we're heading next, along with the strangest twist in this entire story. The machines building tomorrow's quantum computers are increasingly being designed by artificial intelligence itself. Here's the twist that even most tech commentators haven't fully caught up to yet. The race to build the machine that could break the internet's encryption is no longer being run by human researchers alone. Artificial intelligence has quietly become one of the engineers in the room. Just yesterday, July 10th, 2026, Google published new research showing something that sounds almost mundane on the surface, but is in practice a genuinely strange milestone. Their team demonstrated a version of the Willow processor that continuously learns from its own errors while it's actively running. Instead of stopping to recalibrate the way experimental quantum systems normally have to, an AI system watches the error correction data stream in real time and quietly adjusts more than 1,000 different hardware control settings on its own, microwave pulse strength, frequency, coupling parameters, without a human ever touching it. The result was a processor that stayed stable roughly 3.5 times longer under simulated hardware drift and cut its logical error rate by around 20% compared to standard calibration. The researchers are careful to say the machine isn't redesigning itself or inventing new algorithms, but it is, in a very real sense, learning from its own mistakes and correcting course, unsupervised while the computation is still happening. Sit with that for a second. This is not science fiction shorthand. This was published this week, and this is just the latest link in a much longer chain, because the pattern behind the scenes is now impossible to ignore. Better AI helps design better quantum hardware, which, once mature, will accelerate AI training in ways classical computers physically cannot. A faster AI then improves the next generation of quantum machines. Each loop shortens the gap to the next one. We are only at the very beginning of that cycle, and the people inside the field are already talking about it in private in ways that sound almost uneasy. One researcher who left Google's quantum program to help co-found a rival quantum startup reportedly told a colleague still at Google that he'd been using AI in his research and was seeing lots of crazy results. Not promising, not encouraging. Crazy. That's the word insiders are reportedly using with each other right now, not in a press release, but in private conversation. Google isn't slowing down to process any of this. It's widening its bet. In March 2026, the company announced it was expanding beyond its decade-long focus on superconducting qubits by launching a second hardware track built on neutral atoms, individual atoms trapped and arranged with laser tweezers, a fundamentally different approach to building a qubit. Google brought in a physicist from the University of Colorado Boulder to lead that effort, running the two hardware programs in parallel rather than betting everything on one horse. The company's stated focus right now is what it calls Milestone 3 on its published quantum roadmap, a long-lived logical qubit, the stable, error-corrected building block that a genuinely large-scale machine would eventually be built from. Google's original 2019 roadmap laid out a 10-year path toward a machine with roughly 1,000 logical qubits, built from around 1 million physical qubits. Willow currently has 105. That gap sounds enormous until you remember the shape of the curve we're actually on. Every added qubit doesn't just add a little capability, it doubles the machine's computational space. That's not linear progress. That's the nature of an exponential. And exponentials don't respect polite 20-year predictions. They keep collapsing into sooner than expected. Which brings us to the part of the story that stops being about physics entirely and starts being about power. Historically, breakthroughs at this scale reshape which nations lead the next era, the way the race to split the atom or the race to reach orbit once did. Multiple American quantum companies are currently working at the individual, competitive level. Meanwhile, reporting this year has pointed to China concentrating enormous state-directed funding and its top research talent into a single coordinated national quantum effort, treating the technology less like a corporate R&D bet and more like a strategic national project. Whoever crosses the finish line first doesn't just win a scientific medal. They gain a meaningful head start on the master key to a huge share of the world's protected information. And that's really the note this story leaves us on. Because right now, in July 2026, two timelines are running side by side. And nobody, not Google, not Washington, not Beijing, knows for certain which one arrives first. In the optimistic version, quantum computers built like Willow help design new medicines at the molecular level, unlock materials we can't currently imagine, and crack open scientific problems that have resisted us for a century. Google has said plainly that this is the mission driving the entire program. Real-world applications in medicine and material science that are simply out of reach for classical computers today. In the more sobering version, the coming years look like the largest coordinated migration in the history of information security. Banks, governments, hospitals, and companies worldwide racing to rip out and replace their cryptographic foundations before a working quantum computer catches up to them, all while adversaries who've already been quietly harvesting encrypted data cite and wait for the day that data becomes readable. So here's what I'll leave you with. If the company building the most advanced quantum machines on Earth moved its own security deadline forward by 6 years, what exactly do they know that hasn't been published yet? If insiders are privately describing crazy results from AI-assisted research, how much of the real progress is happening behind doors no journalist will ever be allowed through? And if data stolen today becomes readable tomorrow, the real question was never whether your secrets are safe right now. It's how much longer they'll stay that way. The countdown toward 2029 has already started. The people closest to this technology are already moving. The only real question left is whether the rest of us look up in time to catch up, or whether we find out the answer, the way most of history's biggest shifts get discovered. after it's already too late to do anything but react. If this kind of story matters to you, subscribe, because the next domino in this chain is already falling, and you'll want to be 7 minutes ahead of everyone else when it does.